Dr. Sumit, and I'm very pleased to have our alumni here. So I would first request our student coordinator, Mr. Ishan, to have a brief introduction.
Hello, ma'am. Am I audible?
Yes, Ishan.
Yeah. So good afternoon to one and all present in this meeting. I, Ishan Srivastav, on behalf of Electronics Design and Innovation Club and the Department of ECE, extend a warm welcome to you all attending this session of the Amity Global Alumni Forum on the topic Piezoelectric Energy Harvesting, an incredible solution for IoT. To quote Mr. John Maxwell, a leader is the one who knows the way, goes the way, and shows the way. And among us is one such leader, Mr. Sumit Balguhar. Apart from being a 2013 alumni from the same college, he is currently a lecturer at the Eastwick College in Nutley, New Jersey. And before that, he was a senior project scientist at IIT Delhi from September 2020 to February 2022. And apart from that, he was a research associate at IIT Delhi, electronics engineer at Academy of Embedded Technology, and organizer of many e-workshops and seminars and lectures. In order to kickstart this event, I would like to now invite Dr. Pradeep Kumar, Professor and Deputy Head of Department, Electronics and Communication, to say a few words.
Yeah, thank you, Ishan. Good afternoon to one and all present here. And it's a great pleasure for me to welcome our speaker, Dr. Sumit Balguar from Etwick College, New Jersey, US, and alumni of EC department batch of 2011 to 13. And if I remember, Dr. Sumit has completed his MTech in EST from EC department. So thank you, Dr. Sumit, for accepting our invitation and sparing your valuable time and joining us. And we all are very happy to see you here. And alumni like you are the asset for EC department as well as for asset and MED University. And you are just a role model for the junior student because you have achieved a great success in your career. If I'm talking about the topic of the today's talk, so the topic of the today's talk is piezoelectric harvesting, an incredible solution for IoT. This is the topic in which we should all be deeply interested. And as you all know, the global energy crisis and environmental pollutions caused mainly by the increased consumption of non-renewable energy sources prompted researchers to explore alternate energy technologies that can harvest energy available in the ambient environment. And that's the topic of this, the piezoelectric energy harvesting has received the utmost interest by the scientific community. And, the piezoelectric can be harvested to convert, the working motion from the human body into electrical power. And there are many ways are there. Wearable devices can be used for monitor, the vital, we can say the vital physical and psychological sign remotely, as well as for interacting with the computer also. So there are lots of applications are there. So the topic of the today's talk is very interesting and it's very relevant to all the EC students. And I hope you all will enjoy the session and learn a lot. So welcome once again, Dr. Sumit, for joining us. And now it's over to you, Mr. Ishan. Thank you.
Thank you, sir, so for your knowledgeable words. So I would now invite Dr. Sumit to address the audience.
Thank you, Ishan and Dr. Pradeep, for the introduction and having me here. So I'm going to share my screen so that without more delay, we can start today's talk. I hope the screen is visible to you. Anybody please confirm me?
Yeah, it is
I think it's
appearing.
coming. Yeah, it's coming.
Okay.
Not yet, but I think it's coming.
So good afternoon, everyone, and a good morning from US. So thank you for the introduction again.
Morning.
Yeah. So as Dr. Pradeep has already mentioned, about a lot of the advantages and the dire need for energy harvesting today. So let's start with the topic piezoelectric energy harvesting, an incredible solution for IoTs. So IoTs, Internet of Things. I hope you.
Dr.
Yeah.
Sumit,
Screen isn't visible yet.
your screen is not visible. Sorry to interrupt you.
It's
I think
blank.
your screen is not visible.
Plan.
Means we can see that something is shared, but it is not shared. So
Maybe
I think
because
you
of some
can
children.
share it again.
All right, ma'am.
Yeah, you can unshare and then share it again.
Okay, so
Yeah, now we
is it
can see.
visible now?
Yeah, now we can see the
It's
screen.
visible now. Yes,
Okay.
Yes.
Thank you, sir.
perfectly fine. You can start now.
Yeah.
Yeah. So the Internet of Things. I hope this word you already know. So, and it is showing the different component of the Internet of Things. We used it for the data transmission, processing, data analysis, and it is required when we have to do any kind of predictions, right? So, in simple terms, connecting everyday devices to the internet for the analysis or taking any data known as Internet of Things. Okay, being an embedded engineer or electronics engineer, if we go deep into the Internet of Things, what we will find? We'll find, right? We'll find some kind of circuit is there, sensors are there. So this figure is showing you one circuit developed by ST Microelectronics and which has the different components like the analog and mixed signals circuits, which is the backbone of any electronic circuit. It has some sensors and it has some ultra low power connectivity as well as the smart energy management. Okay, so these are the backbones mainly for the Internet of Things. And if we try to deploy them, okay, either for the wired or wireless sensor network. So let's see with figures. So suppose this is the one of the application where we can use these sensors of network for the smart cities. So there are a lot of things. Our railways there. We have a drone, we have cart, shopping center, we have a phone. Everything is connected, right? So just think about the picture you are seeing on your right. Low battery power, right? So what things comes in your mind when we see this symbol on our phone, tablet, or laptop, anywhere? So even we are connected. It's an example for the this Internet of Thing. If my battery will not exist for a long time, okay, then there will be a disconnection. Okay, so that's the reason we need this energy harvesting for IoTs, smart cities, and wireless sensor network. So this is from the application point of view or user point of view, and this is showing the energy harvesting system market by 2028. As Dr. Pradeep has already mentioned, there is a growing need for this renewable energy or the energy harvesting, and day by day, year by year, it is increasing. And by 2028, each and every nations are working in the same directions. So let's start with the energy harvesting. So energy harvesting is not new. It continues a decade ago with the water wheel and windmills and continues to date. Why? Because the concept of clean and green energy is so appealing. And if you look at the basic definition, it's a process of capturing and accumulating energy from the ambient sources. If we talk about the ambient sources, we have vibrations generated from the structures, from the machines, or from any devices. We have a heat, thermal. piezoelectric energy harvesters are there, and we have the solar power as well. So this is the picture which is showing the available power from the various sources. The first most famous is the sunlight, the natural source. And as per the literature, it is giving 100 milliwatt per cm square power, and it is further reduces to 100 microwatt when it comes to the indoor application. Still, there are some drawbacks. Its performance depends on the weather, and which is reduces on the cloudy day. Next, we have the thermal energy harvester. But again, it is difficult to obtain a significant temperature gradient over a small thickness device. Your output, the things which you are going to harvest depend on the designing of your device. And the significant temperature gradient is very hard to achieve. And the third category comes the vibration-based energy harvesters. Since vibrations are the widespread sources of energy, and there are merely three mechanisms to convert the vibration energy into electrical energy. The one is electromagnetic, and that is electrostatic, and third one is piezoelectric, and which is the hot topic nowadays, piezoelectric. So this is showing the basic mechanism, how the electromagnetic, electrostatic, and piezo works. The advantage of piezo is that it doesn't require a lot of your equipment, right? We'll discuss it in the upcoming slides. First of all, let me tell you about the piezoelectric material a little bit. Piezoelectric material comes under the smart materials. And if we look at the definition of the smart materials, these are the materials which possess the ability to change their physical properties in a specific manner in response to specific input. And these are called smart due to their quick response to any specific external stimuli, such as pressure, temperature, electromagnetic field. And this is the table which is showing different types of piezoelectric material. If you have heard about it, thermoelectric is there, electrological, magnetostatic, and the shape memory alloy. Shape memory alloy is a kind of smart material. If you have this material, you put it in any shape, okay? But if you again give some light to them, they regain its shape again. So today we will focus on the piezoelectric material, right? So what is piezoelectricity? So there are two words, piezo plus electricity. The piezo Greek root means pisen means to press, and electricity is a Latin word electrum charge. Means when we apply some pressure on piezoelectric material, it produces some charges. And if we try to collect or store those charges, that's the thing we call piezoelectric energy harvesting. So these are some commercial forms of the piezoelectric materials. They come in ceramic form, and these are their chemical name, lead zirconate titanium. And another is they are also available in polymers form, like PVDF, polyvinyl difluoride. So accordingly, they have some advantages and disadvantages. Like the ceramic paste, they are high, they have higher strength, they are stiff, but they are brittle in nature. And the polymers, they are very flexible. You can make any curved surface. So you can see the next example of Duract and the microfiber composite. Can you see it? So you can turn it. So for people are using it for any curved configurations. So let's see how does this piezoelectric energy harvesting works, right? So there are mainly the two effects of the piezoelectric material. Suppose this is your piezoelectric patch, or you can call it a piezoelectric sensor. If we give any kind of pressure to them, they will produce some charges, okay? And converse is also true. If you apply any kind of electric field, there will be a changes in the structure itself. They will either elongate or contract. Okay. So piezoelectric material are anisotropic in nature. Anisotropic mean their directions are different. Suppose you are giving your input through along the length, you will can take the output from the different direction, that is the height, through axis 3. So according to or as per their nature, we can use them in different kind of configuration. And I'm going to share the two most popular configuration of using the piezoelectric material. One is the we call D31 effect. D31 means you are applying your input along the line, that is direction 1, and taking your output along the thickness, that is direction 3. So you can see here, suppose if there is any structure, if you are bonded your PZT patch like this, then according to this equation, we will get our charges. And you can also explore it in D33 form where the directions of your input and output is the same. So as Dr. Pradeep mentioned about, we can harvest the energy from the motion. So the D33 configuration can be used when we want to harvest the energy from walking, from dancing, or you can put this sensor on your arms, and if you wave anything like so, charges will be produced. The challenge is to collect those charges and to store them and to use it finally for running any wireless sensor node, and that is the main unit for IoTs, right? So today our presentation will be limited to the structure vibrations. We have done some work on motion energy harvesting as well, but it will not be covered in today's lecture, right? So these are some we call it constitutive relations for the principles of piezoelectric material, where S is the stress or a strain, D is the dielectric displacement, and finally this is the equations we use for harvesting the energy. See, where these are the symbols like D31H, Young's modulus. So this table is showing the meaning and the units. So we can see since H is the height, so your output depends on the height, that is the thickness of the material. Your input, your sorry, the output from the PZT depend on the strain and the Young modulus, and the most important factor is D31. That is, we call a piezoelectric coefficient. Okay, whether it's a D33 in case of D33 effect, D31 in case of D31 effect. So if we try to make the nano generator or any device, so that is this is the most important factor, the conversion factor. How much if we are giving any kind of force, whether it's a Newton, millinewton, or any force, how much charges or the voltage we are achieving. So a lot of nano engineers, like people who are working in the nanotechnology, they are trying to make and improving this factor D31. These are the practical applications where we can use it, such as conditional monitoring, especially the structure health monitoring, because this is the one of the field I explored during my PhD work. And you can even use it for the medical implant. You can there are a lot of application of piezoelectric devices in biomedical, and it is also applicable for the automotive of your cars, the tire pressures everywhere. Okay, now let me give you a feel how this entire process works. Suppose this is your any structure or any object from where you are getting the vibrations, and then you have fixed your piezoelectric material to that structures. Now this structure or mechanical energy will be converted into electrical energy using the PZT patch. Since it will be a AC, we need some kind of circuit regulations, rectifiers, capacitor, and sometimes we use some in addition to any other conditioning circuit like boost or buck converter booster sometimes needed. And finally, the main thing is to store this energy into a battery or into a capacitor. So finally, we can run any sensor node or any device. It could be ADC or microcontroller, anything. So this picture shows like there is a possibility for the self-power devices or self-power network. And that's why piezoelectric is an incredible solution, or we can use it for running our perpetual IoTs. So what are the technical challenges and what are the room for improvement? So you have seen here the structure configuration, electronics involved, piezoelectric material itself. So you can do research or read about anything. You can improve in anything, like you can improve in the configuration of the structure. This is the cantilever. You can use the curved shape. You can design them at nano level, or you can explore the electronic circuitry, or you can make your IC a very small so that you can deploy them anywhere. But the challenges are, if you try to make a very compact or very small device, a harvester, then the frequency, which is a very important component or a parameter you have to consider for the design point of view, will increase. So there are many techniques people are working to uh, play with this frequency, either frequency up or down. They are making some linear harvester or non-linear harvester. Some people are making the arrays of harvesters so that if we have a if we are putting a lot of harvesters on in the field so that we can get more energy. And obviously the mainly the circuitry part, which is the backbone for running, for capturing, converting, storing, and finally running your application. People are engaged also in improving the circuitry part. So during my PhD, uh, what I tried to fill as a research gap is, so this the table on your left is showing the comparison of the harvested power from different extraction circuits. But the people were considering the very high frequencies, and the most of the studies were limited to the laboratory. And since I was exploring the smart cities application and the structure health monitoring, so we studied the vibrations of a real structure, and the right table is showing the frequency exists in real-time scenario. So if you look at this table, it is maximum from minimum is 1 hertz and maximum is 15 hertz. And see the frequency of the left, it is in 200 hertz, and many circuitry or harvester which have been designed by many researchers, they achieve to make a mini harvesters, but since because of the frequency is very high, so they are very limited. They face a lot of problem in launching their products in the market. So this is the figure which is showing the assessing of the actual voltage and the vibrations and the frequency content we are achieving from the real life structure. This is the figure of a flyover which is situated in front of IIT Delhi. So I did my study here. So we placed the accelerometer here and tried to measure the acceleration level and figure out the frequencies and the voltage. So this is the acceleration we measured, and using some formulas we converted into the voltage In case if we mounted our piezoelectric material directly to the vibrating structure, then it came around 1.5 to 2 volt. And the first mode of vibration, they were vibrating at 4 hertz. So with this first hand information, we try to make our harvester circuit or try to optimize our circuit so that we can achieve or harvest the minimum or the maximum energy so that we can run any real kind devices, right? Then with that first hand information, we did some laboratory study by considering the vibration generated from these different kind of shakers. This is this energy harvesting kit from Smart Material Corporation, and this is the MFC microfiber composite piezoelectric patch developed by NASA. And this is the shaker table. We used different kind of shakers to produce different frequencies and the voltage, and which have the similar component or signal which we measured from the real structure. And this is the air conditioning cooling plant. If you ever get a chance to closely visit any kind of big machinery, you will feel a lot of vibrations. And many these industries uses dampers to suppress those vibrations. So for them, these vibrations are waste. But for us, this is a waste energy which we can convert into some usable electrical energy. So we started with our harvester kit and try to produce with this similar kind of signals. And with basic rectifier circuit, we find out that Schottky rectifier circuits are better in comparison to the silicon diode. So this is the table. You can see the two devices here. One is ADC from Texas Instrument. Another is the another sensor is carbon monoxide sensor from Microchip Technology. So in laboratory, we could harvest some energy that can run these devices, but see the charging time and the charging cycle. For running this ultra low power sensor, we need charging cycles in lakhs, 2,30,000, and almost 28 days of continuous charging can run this device only once. So our objective to reduce these charging cycles and charging time so that we can run these devices and connect it to our IoT so that it can capture the real data and transmit from one system to another. For this, we explored a lot of configuration from the circuit point of view. Mainly, one is the made from the diode. We made this diode based rectifier circuit using BAT diodes, and another configuration we explored based on MOSFET rectifier, where this gate cross coupled and fully gate cross coupled were realized. So these all were passive and a discrete component, because the main challenge for in the field of energy harvesting is you can't use any amplifier. If you use any other power source, then your entire purpose will be defeated, right? Because you have to harvest the energy, and from that harvested energy you have to run a device. If you use any other auxiliary power source, then there is no use for researching or exploring this field. So that's why we limited ourselves for the passive things, passive circuit only. Then after doing during the optimization of this circuit, we found that the diode based rectifier which made of this model, we achieved the maximum efficiency around 81%, And the most important point is at the minimum, we are calling 1 volt 5 hertz minimum as per the things we measured from the real life structure. If we say the minimum voltage or minimum hertz, so you can go into 0.1 hertz as well, or volt, you can go into millivolt. So there are a lot of ICs are available in the market which even work on zero point 0.7 and zero point 0.3, right, volt. Then our next purpose was to, after optimizing the circuit in the laboratory, to do the field experiment again. Then we went to the field again to check the suitability of this circuit and to harvest the energy. Till now, if we see the table of technology readiness level on a scale of 9, the research in the field of piezoelectric energy harvesting was on 6. I think I missed the slides of technology readiness level. So in 6 means it is mostly limited to the laboratory, and there were only few limited studies uh, were done by the researchers in the real field so that they can capture the energy. So this is our experimental setup, our rectifier circuit, and we try to charge a NIMH rechargeable battery. So the other new things we did, so far people were working on the different kind of configuration, and we call it a secondary structure. See, this is the piezoelectric material. We are bonded it to our structure. Suppose this is the secondary structure, and this secondary structure is fixed to the primary structure. This is the girder of the bridge, right? So before bonding our piezoelectric material directly to the primary, we did this pilot study, and these were the output voltage we were getting around 6 to 8 volt, and the frequency content is again 4 hertz, which we measured before starting our research. Then we tried to bond our piezoelectric material directly to the structure. So this is the new thing we did. We directly bonded our structure. These are the steps. We covered it with magnet for curing. Now just imagine the situation. How did we bonded it to the very high elevated corridor? We did the experiment again on the flyover, and we're working underneath. Okay. And we did soldering there, covered with the epoxy for protection, and it was not achieved in a single one trial, right? We did a lot of trials, and you can see this is the close-up of the broken PZT. If there is a lot of tension, I hope you know about the our structure works like this. A lot of tension or compression is there, your PZT will break. So this is the main challenge, to bond this piezo material directly to the structure and then capturing the energy from them. Finally, we succeed, and this is the output voltage we were getting. So this is in the uh, close vicinity which we initially measured using the accelerometer, and this is the frequency content, again 4 hertz. And in addition to uh, this we call the PZT patch, and we procure it from PI ceramic. All right. And another configuration we used piezoelectric material, that is MFC, macrofiber composite. See, macrofiber composite, it is more flexible. So we also bonded this one so to measure and to see the effect, which one will be long lasting if we use them for direct bonding to bond it to the structure. And this is the output voltage you are getting and the frequency content. And this the strain was in micro strain, and we were getting around 3 volt. Then using this circuit, this figure are showing the charges curve of our battery, the upper one, and we discharge the same battery through a load of 4.7 kilo ohm resistor. And The battery was charged to the final voltage of 1.62. Final voltage in the sense when it achieved the maximum steadiness. So it took around 7 hours. And that energy level, if we use for any load, it can give a power around 6 hours. So you can see if you try to charge your iPhone, so it will not take 7 hours. The reason being because of the discontinuity when the how the vibrations will be generated when vehicles will flying over the bridges or the flyovers or any street, then this vibration will come. That the vibration will be transferred to the girder, and on a girder our PZT is there. Then after PZT we have our circuit. So there were a lot of losses even, but we didn't consider all these things because our purpose was to capture energy from the real life vibrations. So yeah, we achieved it. So and this is the graph for the case of MFC PZT patch, and this is piezo. So you can see from the ceramic based PZT, the voltage we achieved is very less in comparison to the MFC and to the secondary structure. It's all because of their part density, their size. It matters a lot. And we also tried to charge the capacitor from the PZT patches. So now let's see the table again, which we tried to improve in the beginning. So this is the same table. We had this ADC from Texas, microchip carbon monoxide sensor, and finally even we didn't like reduce the charging time and the cycles for these two. Even for we could run a real-time device which is AD5933 developed by Analog Devices. This is the chip engineers people are industry people are using for the condition monitoring. They took this device to the field, and through some mechanism they capture the signal there, the healthy and unhealthy signal, compare them and tell about the conditional monitoring. Yeah, how much our structures are safe. So we tried to replace this dependency on these kind of circuits or dependency on our battery. If we have any IoT based where we have this energy harvesting unit and we can deploy them in any structure. So since they are self-powered, they can harvest the energy, and only 6 hours charging is sufficient for their one-time operation. Okay. So this is the comparison between the energy we harvested in the laboratory and the field. It is approximately same, though the input voltage is higher in case of field, but since it was not a controlled parameter, it was not in our hand, these laboratory parameter we can control. And though this input voltage is high in the field, still we achieve that much power and a long time. Again, the reason because of the discontinuity of the vibrations. So this figure table is showing the energy harvested from traffic induced vibration. So showing the comparison between MFC and PZT. So in a nutshell, charging a battery from the real life structural vibration has been demonstrated, which marks establishment of technology readiness level of 7, which is the a major original contribution. Then we again try to try to harvest the energy or charge our battery from the wind induced vibration. So this is the wind tunnel made in our laboratory. You can see this is the fan through which we were giving air so that our structure can vibrate. I'll show you the better figure. Yeah, it is there. So this is the the setup just to anemometer to measure the wind velocity. Yeah, this is the structure we made, a cantilever and a triangular connector, so that for giving the more thrust. These are the symmetrical and material properties of this structure. So we consider only the two cases when the speed of a wind is high or low. When we say low, it was minimum 1.6 and maximum was 3.2. And these are the output voltage we were getting from the piezo from this wind induced vibration, and the frequency contained was same as we were expecting from the real life structures. And with this setup, the battery charged again to 1.9 volt and took around 7 hours. At the this is at the maximum speed and 0.44 at the minimum speed, and it can again power a load of a resistor value for 4.7 for 6 hours and 1 hours. So experimental result shows that it is feasible to charge a battery under low frequency 5 Hz or less and a small voltage scenario for case of structural vibration by employing optimized D1000 rectifier circuit, and power in milliwatt range can be achieved. And in a nutshell, charging of a battery from the real life structural vibration has established. Yeah, this is the table for the technology readiness level, especially for the field of energy harvesting. So it is on a 9 scale. So earlier the studies were limited for the integration level, showing system function in lab test. After the studies, we have achieved or jumped directly from 4 to 7 the demonstration of complete system in operating environment. Operating environment here in the field environment. So based on the current work, let me share with you. So based on this research, I received a grant from Dholera Industrial City Development. So this is the first smart city developing in India under the direct supervision of our President Shri Narendra Modi ji. So I got a grant on it. So these are the studies going on there before moving to the US. This is the site where we are trying to embed the concrete vibration sensor. This is the sensor developed in our lab, and we received a patent for it. And we have advised them to embed this kind of sensor where they want to harvest the energy from the vibrations. And they are making a very high-rise building in Dholera. Dholera is in Gujarat. So where we can, this is the just for demonstration, we can put a different kind of these arrays of sensors, so that from the wind as well, from the traffic and wind as well, we can harvest the energy and use them for lightning or any things. Apart of this, I have a collaboration with Central Road Research Institute, which is in Delhi. It is on Mathura Road if you go from Ashram to our MT University. So this is the research we are doing from the configuration point of view. If we could make any tile so that we can put it into a field, if you walk or dance on them, we can harvest or capture the energy, right? So these are the pictures from the preliminary test. So our setup, we use different kind of vehicles over them. So in the previous study, we had no control on the traffic flow. Here, we did the study where we can control the vibration, we count the axle load and everything. And after the in-house experiments, we finally install them on the Mathura highway. So this study was done in October 2021. This is I am with my CRRI team, and this research has been covered by G News on the day we were installing them. So the purpose is the same. When vehicles will pass over them, we can capture the energy and to run any electric. So this project is still going on. Now, thank you for listening. I hope I have not taken much time. Uh,
Absolutely not, Dr. Sumit. It was very interesting research. And I would ask the students if you are having any queries. Yes, Sagar has raised the hand. Sagar,
Yes,
you can unmute yourself and
good evening, sir. Some query is how is IoT important to the from the industrial point of view, like how we can benefit from the IoT in the industrial 4.0 that is we are planning.
okay, IoT is important from industrial point of view. See, if you talk about any, we all are electronic or embedded engineer. We people are designing it, okay, in industry. And why it is important? Because nowadays everything is connected to the internet. Even now, people are working. See, in the US even because due to the corona, India uh, from the physical platform they come to this online platform, but in the US this country already you can take your appointment, you can book your appointment through online system. And see, since these all these systems are connected through the internet, so this is the very important. IoT is the future, and to so that they can run perpetually, energy harvesting is the backbone, electronics is the backbone. And if we talk about the IoT, there are a lot of components. It's up to you which field you are going to explore. Whether you are going for a research in future or whether you join as an electronic or embedded engineer in industry. It's up to you. Whether you can improve the data transmission, you can improve the connectivity, or you can work on the optimizations of the circuit, you can reduce the timing, anything. So from all point of view, whether you are in industry, from industrial point of view, from academic or researcher point of view, it is very important.
Thank you, sir.
any other query?
Is there any other question from student side?
Okay, Mr. Ishan.
So thank you, Dr. Sumit, for you have delivered a nice, informative, and wonderful talk. And the best part of this talk is the topic was very interesting because these kind of energy harvesting system, in future we'll see everywhere, starting from the healthcare monitoring system or maybe biomedical applications, maybe smart city development, and everywhere you can see these kind of systems are very much required. And as you mentioned during your talk, the best part of these systems are here we are basically converting, the waste energy into the useful energy. So that is, the best part of these kind of systems. And these kind of systems are very much required because this will help and, will make the life easy of everybody, every person in the future. So that's why your talk was very interesting. You have covered all the concepts starting from the basics, then design, implementation, as well as you have shown the laboratory setup, etc. And you have discussed the real time real life applications also. So your talk was very informative and it was very wonderful. And I hope, I am very sure our student has gained a lot of knowledge and experience through this particular session. So thank you once again for sparing your valuable time and joining us for this important session. So thank you again, Dr. Sumit. Thank you. It's over to you, Ishan, Mr. Ishan.
Thank you, sir. So this was indeed a wonderful and very insightful session about the use of piezoelectric energy in the field of IoT. And I hope that many of our attendees would have learned many things about this. And to end the session, I would like to invite Dr. Nidhi Kaur to say the vote of thanks.
Yes, thank you, Shan. So I would be, first of all, I'm very thankful to Dr. Sumit for sparing so much of time, and I'm very happy as well to see the student whom some years back we taught here, and he is there in the campus as the other attendees that we find now. So with this, the students can have this thing also, that they can, the students who are attending the session now, they will be like in future they may be sitting like you, and they will get inspired from you. Also, the most means beneficial thing which I liked about your talk is that you talked about the practical implementations, not rather than about the theory or so. You have shown everything practically. What you did, you have shown the actual implementation which is there in the field, so that students can also learn that sometimes when students learn with the book, they will see that if this thing exists or not, but when you see the practical implementation, you will understand, no, no, this is here and we can implement it, and we find a way to means where to go for the future, because these students are just in the bachelor's degree, so they are more towards in a generalized field, so they will find or they will get motivated for one or the other field. As you said that this is up to you that which field you need to choose. So this was a very wonderful session, and I'm very thankful as well as very pleased to have you here. And we are having alumni meet also in few days, so we are expecting alumni like you to be the part of it. I think we have already given you a formal invitation, so from this platform also I am inviting you for the alumni meet, and hope to be associated with you in future. And if you find any, like if you find any kind of possibilities for research collaboration, then you are very much welcome. We have few students, if they are interested, then we can be means we can have certain collaborations like the internship or so with you. We can plan for such kind of things as well in future. So looking forward for such association, so that we can have a long association, like university to university, and even now UGC has given this, like we can have some inter-university associations as well. That would be very nice. So
Thank you,
yes,
everyone. Thank you, ma'am,
thank you.
sir. And ma'am, last message I would like to give to the students. Student, just I want to share, like I was Nidhi ma'am taught me networks, ma'am, right?
Yeah, and
So I
I'm
just want to
teaching
let you
networks to
know,
them as well.
yeah, you have the best teachers. So don't think that you are lacking of any resources. You have the best institution. You have the best teachers. These teachers, I have like these. I like when I was a student like you, so I was dreaming something like one day I will do this kind of research. And these were the teachers, they were motivating us by organizing this kind of lectures. So don't miss their lectures, these kind of special guest lectures as well. And definitely you can be a even a more great speaker for us one day. So believe in your institution, believe in your teacher. So that is my advice. Just that's the message, ma'am, I wanted to give. And sir, thank you
Thank you
so
so
much.
much. Thank you very much. So, with this, I would like to end the session, sir. Shall we?
Yes, yes, we can. We can now. We can proceed for the
Okay.
ending.
Okay. So, thank you, Sumin. Thank you for sparing the
Thank you,
time.
ma'am. Yeah.
Thank you all
Okay.
once again. Thank you.